right, so hello everyone, my name is Jason Molgard. I'm a Principal Storage Solutions Architect with Solidigm, and actually some of what I'm going to talk about ties in very nicely with what Anil just presented in terms of a device that has both NVMe and memory. So my title of this presentation, Host Addressable Subsystem Local Memory. So I don't know if anyone is familiar with subsystem local memory that's been defined in NVMe, but it's a method of having memory in the device that's specifically for computational storage, but actually could be used for anything. And that's an enhancement that we are working on is what I'm going to talk about. So briefly for the agenda, so I'll describe what it is or why we would do it, how it would work, some benefits, and then we'll take a look at use cases, which are all computational storage related, but again, it doesn't have to be. All right, so why would we want to be able to access subsystem local memory using host addressing? So this is memory in the device that historically has been private to that device, and now we're going to open it up and give it a host address. And as it stands today, through SLM, the devices are already having a lot of host accessible memory. So it can be accessed with the commands that are defined in NVMe in terms of the SLM command set. So there's a memory read, a memory write, a memory copy, for example. And this is another method of being able to access it. And so if we enable a memory protocol, it would be more efficient to access that memory. We can do peer-to-peer communication using a memory model. And of course, if we configure that memory for CXL, we can have cache coherency. So that really ties in quite nicely with what Anil was talking about in terms of having a device that has CXL connected HDM that's also a storage device. So from a computational storage use case, which is what my examples all reference, but again, not the only, they're going to have more subsystem local memory. So they would quickly be able to take advantage of the fact that there's this memory in the device that we want to have host addressing. And they certainly benefit from peer-to-peer communication. And we'll look at some examples that describe that. All right, so how does it work? So currently, subsystem local memory as defined in NVMe, there's the SLM command set, command access only. So you can use the commands that are defined, a memory read, a memory write, a memory copy, memory fill. Those are the commands. That's what's available today. Moving forward, there's still going to be that option to use those commands, but then two new methods as well. So there'll be the SLM command access and PCIe bar or base address register access, and SLM commands and CXL host managed device memory. So you have to pick one of these three at boot time based upon which way you want that particular memory namespace to operate. You can have multiple memory namespaces in your device, and each one can be configured for one of these different access methods based upon what it is that you want to achieve. So for at boot time, for any memory, any SLM memory that you want to have bar access, the device is going to make a request for bar space. That happens obviously very early in the boot process of the system, so you need to specify very early, I want bar access for this memory. And any memory that we want for CXL, that would get programmed later. The vision is that there would be an NVMe driver that is CXL aware, and that CXL aware NVMe driver would be able to call kernel services and get that HDM memory configured during the boot process. Now it may be that you're building a device or someone's built a device and you want to have it work. The preference is that it runs that the memory is a CXL addressable memory. But if you happen to get plugged into a legacy host that doesn't support CXL, is it just completely disabled in terms of being able to access that memory? Or would your device also function perhaps in a limited basis if that memory had bar access instead of CXL HDM access? So we're trying to build in a mechanism that enables that choice to be made, where you can say, hey, I want CXL, I will accept bar access, which has restrictions, obviously, it's not the same, but at least it provides the ability to have that load store access to that memory, if that it will allow the system to work acceptably. So let's kind of get into this in a little bit more detail with this picture. So we've got a memory map in the middle that shows available device memory. So kind of starting at the bottom, we've got our PCIe base, moving up a little bit higher, the CMB offset, followed by the SLM/bar offset. So this is where we're going to start specifying or requesting, here is the bar address where we want bar to extend for our SLM. And we specifically want SLM namespace IDs 1 and 2 to be bar accessible. This is just an example, so any combination is possible. Namespace IDs 3 and 4, the preference is that they are CXL accessible, CXL HDM. However, for this example, we're willing to accept them as being bar accessible. And there is a vendor out there that specifically was looking for this flexibility so that, for legacy systems, their system would still work. So basically, at boot time, we're going to request our bar space all the way from the PCIe base up to the line that says allocated to bar. So that we make that request for that full amount, even though our preference is that for namespace IDs 3 and 4, they would be CXL HDM. Later on, as the boot process continues, the HDM decoders are programmed, and the device says, hey, I want namespace ID in 3 and 4 to be addressed by CXL. So it makes that request, and assuming the device is able to satisfy that, great, then it does that, and those namespaces are now going to respond to the CXL HDM addresses. The bar addresses, even though they were allocated, they won't respond to that anymore. It's like it's a hole in the memory map for the PCIe bar, but it enabled the flexibility of being able to have it either way based upon what the system would support. And so that's what we're looking at over on the left-hand side and the right-hand side of our memory diagram. The left-hand side is showing, here's the full bar space that we need to request. Some of it is, as it turns out, as the boot process continues, going to be, there's no memory backing that bar space, so it was allocated, but it's unused. And instead, the memory backing it is shown over on the right-hand side, which is the memory backing that CXL HDM space for those namespaces. All right, so I've covered some of these items on the previous discussion, but let me just kind of summarize a few items. So this is work that's happening in NVMe. It's still in the architecture phase. TP4184 is the number. So SLM will be accessible, or is accessible, by both the host and the device, and we're effectively adding a new set of access methods, either PCIe bar or CXL, to the SLM memory as it's already defined. So the SLM memory can be read and written with the SLM commands that already exist. We can use load and store, host load store commands based upon how we've configured it. And of course, if we've configured it for CXL, then we'll use cxl.mem commands potentially to access that SLM memory in the device. Of course, the SLM memory can have virtual mapping for host applications. And that enables the host to, or the app, we don't have to switch context to access that SLM memory. So if you're using this for computational storage, any of the existing mechanisms in terms of computational programs, none of that is changed. Nothing changes. It's no different than the way it was before. All we're doing is adding host addressing to the SLM. And this is going to allow peer-to-peer movement, because now the memory has a host address that it did not have before. It was a private memory previously, and now we're making it a visible address. But through it all, the commands are still valid. They will still work. We're ensuring backwards compatibility with everything that already exists. You had a question.
I had a question. You picked specifically that region defined for computational storage, is there a reason you couldn't include the CMB region?
Well, we're keeping it separate from CMB. So CMB, we don't want to touch it, right? It works, people use it, it's a known quantity. We're adding this in for SLM, which was defined for computational storage as another form of memory that's in the device. And there certainly is a use case for computational storage, and I think there are other use cases as well, but as far as extending CMB, I think that there would be a lot of resistance to breaking something that already works.
So CMB is that command, I'm not so interested on NVMe, but is that the command buffer memory of NVMe?
CMB is controller memory buffer.
Showing there, but CMB is this is where it is, and you don't want to touch it.
Yeah, but we're not going to change CMB at all.
So many things will break.
Yeah. All right, so what are some benefits? Well, I've touched on all these, I think, but let's just go through the list quickly. So with this enhancement, we'll have multiple access methods for SLM. We can, load store provides a low latency, fine granularity path to the SLM. If we enable CXL support as one of our configuration options, then we can have coherency with that memory, and that's certainly going to be interesting. Avoid copies and data movement. Since we can now address that memory directly, we can use CXL to go write it directly instead of, for example, first writing it to host memory and then later DMAing it into the device memory. And then now we can bypass the host for peer-to-peer movement because this is a host addressable memory. So we're enabling two different methods of access, and so what's the difference between the two? And I think it pretty succinctly can be summarized with coherency. So if we have CXL, if we're using CXL, then we can have coherency with the host memory and the memory in the device, the HDM. Whereas if we're using the PCIe bar, yes, you can still use load store to access the memory, but you're not going to have any coherency. It's going to be load store access over the PCIe architecture using uncached MMIO space. So that's where I think that coherency is the key. If you can take advantage of the coherency, then the CXL is going to provide the value. All right, so let's look at some use cases. And actually, the first use case that I have uses CXL and takes advantage of that coherency. So let me kind of describe what we're looking at here by walking through the picture over on the right-hand side of the slide. Basically, we have a host CPU or host system at the top. It's got the CPU, cache, system memory. We have a fabric in the middle. This happens to be a CXL fabric, as this is a CXL example. And then underneath that, we have a computational storage drive, which, like I said, the only benefit is that there's a lot of SLM memory that would go into a computational storage drive, and so it just makes for a great way to show examples. The computational storage drive has all of the usual components that would be required in an NVMe-based computational storage drive. We've got our NVM namespace, our compute namespace for doing computation, and our memory namespace. The picture shows the memory of the memory namespace, the SLM memory itself, the media, it kind of expanded. And that's the orange and yellow over on the right-hand side of the diagram. So we can more easily see what's happening in the memory itself, as that's the focus of this enhancement. To the left is kind of a memory map, a host physical address space map of all of memory for the portion that has been mapped to host memory as appropriate. Okay, so for this example, this is a data post-processing before writing to storage example. So basically we're going to write some data to the drive, we're going to do some kind of computation on it perhaps, and then after that computation completes, we're going to write it to the media, for the persistent media. And so the value proposition is we're going to avoid copying data. So we're going to take advantage of the fact that we can use CXL to move that data directly to the drive, which is useful, especially for small transfers. If you have a very large transfer, maybe it is more efficient to set up a DMA. And so, that's our value proposition for this case. So the configuration is that we've got two buffers. The input data buffer is going to be in Host Addressable SLM, and we've configured it for CXL. The output data buffer is just in traditional SLM. It does not need to have a host address because it's going to be the recipient of our post-process data right before, as kind of a temporary holding buffer before it goes out to the storage media. All right, so if we kind of follow the arrows, which are color-coded based upon the function, in step one, the application is going to do writes or stores to basically to the memory in the device using cxl.mem. So it's going to, instead of writing out to host memory to set something up, we're going to write directly to the device memory. So some of the data, or maybe all the data, may still be in the host cache at the end because we're coherent here. No problem. We'll touch on that in just a moment. All right, so now we're going to issue an NVMe execute program command to go off and post-process the data. So as part of that, because we're coherent, the device needs to use a snoop back and validate protocol to the host and say, hey, I need to have all the data in me because I'm going to manipulate it. So you need to, flush your cache and make sure that I've got it. So we get all the data in the device. Now the device can perform the computation, writing it to the output data buffer. When that completes, now the host can issue an NVMe copy command to move the data or copy the data from the output data buffer to the NVM namespace. So it effectively finishes writing it out to the media, and now it is stored after being post-processed. So use case number 2 is just the opposite and is very similar, but it does highlight another important benefit, especially of the CXL. So same value proposition in terms of the avoiding copying data using a DMA, same benefits of lower latency for small transfers especially. The input and output buffer are flipped, so this time our input buffer is just in traditional SLM. It does not need to have a host address. Our output data buffer does need to have a host address, and so it has been assigned a host address. And for this example, again, we're using CXL, so it's configured for CXL access. All right, so we're basically going in reverse. We're doing a read this time, so we're going to use an NVMe memory copy command to move the data from the NVM namespace to the input data buffer in SLM. Once that finishes, then we can do an execute program command to pre-process that data before we send it back to the host. Again, we can use a snoop back and validate protocol to say, hey, host, make sure your cache is flushed because I'm about ready to edit the data. So it's going to perform a manipulation on the data. And when it finishes and reports back to the host that it finished, at that point, the host can just come and read it using a load command. It can read it directly out of the memory using cxl.mem. There's no need to copy it to host memory and in order for the host to read it at that point. All right, third example. Oh, there's a question. Go ahead.
So, in general, right, in the end, the SLM memory in the device, this data buffer is only limited. So after you do a bunch of these reads, there should be some way for the host to say, I don't need that memory anymore. You know what I'm saying?
So yeah, the question is, when the host is done reading it, how does it say you can free it again? That's a good question.
It's a function of the memory management system within the host. The host owns those addresses, and the host can do whatever it wants with them.
Yeah.
When one part is done using it, then it can use it for something different. It's purely a host
So it will
function.
be part of the NVMe driver or something. In my head, that's what I was thinking.
Yeah.
Okay.
So let me just repeat for the recording. So the suggestion is that it's a function of the host, that the host owns those addresses and can make a decision to release them as it sees fit. And maybe it would be part of the CXL aware NVMe driver or something to that effect. Yeah. All right, so for use case number 3, this is a situation where we're going to do some post-processing with a standard SSD. So we have the picture showing a computational storage processor and a traditional SSD sitting next to it on its left. So this is a peer-to-peer example. So the benefit is that we're going to bypass the host for data movement. Basically, we're going to, in this example, we have both of our input and output data buffers are in Host Addressable SLM. They happen to be configured for CXL. So very similar to example 1, we're going to use CXL.mem to write to the input data buffer. We can use the snoop back and validate protocol. All that's just like example use case 1. When that finishes, and and just like example 1, we're going to process that data and write it to an output data buffer. So when all that finishes, and we've got it in our output data buffer, now we need to go store it over in our neighboring drive instead of in our local drive. And in this case, we're going to have the host issue an I/O write to the traditional SSD, and the data pointer is going to point to the output buffer in our SLM, and it can do that because it's a host addressable memory. It knows where that is, and then we will that write operation will pull the data out of the SLM, write it to the SSD using PCIe UIO for direct peer-to-peer transfer. All right, so one more peer-to-peer example. This is similar. But no CXL in this example. So we have 2 computational storage drives. One could be a traditional drive for actually the use case, but the intent here is we've got data in drive A and drive B, and we need to get all the data over into drive A to perform a computation on it. And so what we're going to do is we're going to issue an NVMe read command to drive B over on the right-hand side. And the destination for that read is the input data buffer over in drive A. So we're going to read the data out of drive B and write it or store it, the resulting data in drive A's SLM. And again, we can do that because the SLM now has a host address. It's just like any other system address. So we read that data into drive A. And maybe the reason we want to do this is drive A contains part of the data that we need for the computation, and drive B contains another part of the data. We need to get them all together into one location, and now we can do a computation on it. So the steps are showing the data movement from drive B to drive A. Just like the use case number 2, we can, if we need to, we can pull some data out of the media on drive A and also put it in the input data buffer and begin then doing computations on it. And that's exactly what we're going to do. We're going to do some calculations, writing the result to an output data buffer that's in drive A. And then once we have the data in that output data buffer in drive A, obviously we can do anything with it. Just like use case 1, we can write it back to the media on drive A. We could potentially, in a different example, we could write it to a drive C that's not shown here. Whatever we want to do with that data after we have completed those calculations. All right, so to summarize, a group of us are working on enhancing SLM to add host addressability. And there'll be 3 different access methods, the commands plus PCIe bar, and commands plus CXL. And certainly, I think there's use cases for all of them. It doesn't have to be computational storage. It's just that certainly is a convenient example given that there will be a lot of SLM in computational storage drives. Lots of benefits. Now we can have load store access to that memory. We can potentially have coherency if we've configured it for CXL. We can have lower latency for small accesses. We can do peer-to-peer since it's got a host address. And no need to copy data if we are, wanting to write the data directly to the drive. And I think this is going to enable a lot of new use cases, not only for computational storage, but other technologies as well. As there's nothing that precludes you from from using this to do other applications where you can have CXL or PCIe bar attached memory in your drive. All right, that's all I have. Paul.
Yeah, one of your slides mentioned PCIe unordered I/O, UIO.
Yeah.
Is that essential to anything you've shown here? I don't really know very well. Is it essential to any part of CXL's use? Or?
So the question is PCIe UIO essential for the operation? And the answer is it's not required for anything that we're doing in terms of enhancing the NVMe and adding addressability to SLM. For this particular use case, and we're writing to a standard SSD, this is one way to make it work, although I'm not sure that's the only way. There may be other ways. I am only loosely competent on UIO, so maybe there's a better expert who could answer that.
And along, if anyone knows, how widespread is the implementation of UIO at this point?
How widespread is the implementation of UIO? I don't either. I have a feeling it's still early at this point.
No, there are no CPUs out yet, right? So a Gen 6 PCIe, so.
Are you looking at the bottom bullet that says UIO can't use bar space?
Oh, I missed that.
Well, because that's comparing CXL to bar. You can't have both CXL and bar.
Right.
So the UIO in that sentence is sort of a red herring.
Yeah.
I just think you could just use PCIe peer-to-peer transfers.
Yeah.
Yeah.
You don't need to ignore UIO.
Right. That could be done with current Gen 5.
So the comment is that we shouldn't need to use UIO. We can just use PCIe peer-to-peer. That's great. Yes.
I'm not sure that's totally true because we're not using the PCIe bar addressing in this example. You'll notice that the SLM is a CXL namespace, so it's addressed by CXL. And my understanding was that the only way that CXL could do a read out of that data space over to the storage is by using UIO within CXL.
No, but he said they're not using CXL in this, right? So that SLM is bar address.
No, the SLM is CXL address.
So in this example, it's
Is
the
UIO CXL or is UIO PCIe?
PCIe.
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 Then
And
it's- Okay, you're right, then this slide is wrong.
And it's optional. So if you don't have it, then you can't use it on CXL or the bar. And if it's present, then you should be able to use it on either one. But it's either going to be mapped through CXL or mapped through bar. It can't be both. My understanding.
Right, that's correct.
SLM can either be just addressed by PCIe bar or by CXL.
Correct. That's
SLM
correct.
doesn't mean CXL only, right?
Right.
That's right.
So
Yep, SLM is not a CXL only.
So the namespace is either, it can either be addressed simply by SLM commands, NVMe commands, or those NVMe commands and CXL, or the NVMe commands and PCIe bar access. It can't be accessed by both bar and CXL.
At the same time, that's right. You'd have to set up two different namespaces.
From boot time, that namespace is.
Correct.
one or the other.
From boot time, the namespace is one of the three access methods, and that's
In this
it.
example, I thought you clearly said, hey, there's no CXL in this. Didn't you say that?
No, in example 4, there's no CXL, but in this example, there is CXL.
Yeah, the second bullet configuration, input is CXL, output is CXL.
Yeah. Was there?
This example, number 6, says it's using UIO. And
Oh, you're right. So CXL peer-to-peer is only using, I think, UIO. That's what they say.
Okay.
if the device supports it. But there's CXL devices today that don't support UIO yet.
Yeah.
But they also don't support CXL.
I thought there aren't CXL devices that exist that
Yeah, they do. but
they don't support UIO yet.
Not backing or either, because that's CXL.
Yeah.
free auto.
Yeah,
But yeah, for sure not UIO, because UIO again is free auto.
yeah.
Was there another question?
Yeah, the TP, does that require driver updates? upstream?
Yes, there will need to be a driver update in support of this capability. And,
But it is backward compatible.
but is backwards compatible,
Existing
exactly.
stuff will keep working. That's
Yep.
the intent.
Yep.
You just can't use the new stuff until you get the new drivers.
Yep.
If we run out of technical questions, I have one that SW Worth pointed out to me. Could you go to the thank you slide?
Okay, yes.
I've already noted that 5 times.
Oh, yeah.
I haven't told anybody, but,
Yeah. Can anyone see the grammatical problem?
yeah, second sentence.
You can.
You get access
The
the.
presentations, yeah, there is a, that is a valid point. There is an error in the grammar for the last slide. All right, well, with that, I'd say that's a good ending point, so thank you.